Okay, hello everyone. Let's pick up where we left off, talking about quantum mechanics here. Okay, so now let's talk about the Bohr model of the atom. Okay, so the Bohr model of the atom. So, so previously, before Bohr, the model of the atom, it was kind of a very muddled picture. It wasn't really clear what we knew about the atom, but what we did know was that um, that if you kind of recall about the structure of the atom before the Bohr model was developed, basically what we had was, so I could kind of draw it here. Let me just draw it. Let's draw it up here. So before the Bohr model, right? Essentially, what we had was a dense nucleus in the center, and around it was the atom was mostly empty space. So let's assume this is a sphere, okay? And then surrounding the so surrounding the empty space of the atom, or surrounding the nucleus, was this empty space, and we consider that to be what we call the electron cloud, right? So here's the electron cloud, and here is the nucleus. So, the proposed. So this was proposed, or kind of what we thought the model of the atom was by Rutherford's gold foil experiment. And that's what established the nucleus. And then there was the pudding model of Thomson, which established that electrons were negatively charged. So at the time of Rutherford, what happened was that we knew that there was charged particles. The electron had a negative charge, and the nucleus had a positive charge based on these experiments. Okay, so what ended up happening? Bohr then took this model, and then he kind of ran with it and tried to explain that the electrons are actually not. He tried to kind of go deeper into saying that electrons are not simply around the nucleus, like in a sea of electrons. They're actually more localized than we originally thought. Okay, so this was before Bohr's model. Okay, so we're going to say model of atom before Bohr model. So the problem with the model before this model, is that it didn't really explain what the electrons were doing, or it kind of didn't explain exactly where are the electrons, because it didn't make sense that the electrons occupied the space around the nucleus. Because in Rutherford's experiments, he noticed that most of the particles that he shot through the gold atoms, they were mostly empty space. And what happened? So it didn't really make sense that electrons were just surrounding the atom, because eventually he would have saw in his experiments that they could have collided with the particles that he shot at the gold atoms, but he really didn't observe much. What he did observe is that the atom is made mostly of empty space, and that at the center of it is where most of the mass of the atom is, and that's the nucleus. Okay, so those are the two contributions before Bohr's model. So now Bohr's model is a little more. We kind of go a step further. So at the center of the Bohr model is the nucleus. Okay, and around the nucleus we have what we call energy levels, principal energy levels. So we have a level that's closest to the nucleus, a level that's outer, and then we keep going ever so closely. Then eventually you get to a point where the electron levels, they're going to get increasingly further away from the nucleus. So in this case, we can say at this, let's point at the first line here. That's the n equals 1 level. N equals 5, okay? So what Bohr proposed is that these single lines we see in the hydrogen spectrum, they are of distinct energy. So electrons can only emit this. The electrons can only emit this energy if they absorb a specific quantity of energy. That's why the energy levels are lines and not a continuous spectrum. So the amount of energy in the hydrogen atom, the electron energy levels, they're not all the same. So they're different. And what he suggested that these energy levels are what we call quantized, or they are of specific energy. They are not continuous, where any amount of energy absorbed can emit. The electron can emit it back. In every energy level. So these energy levels have specific energies. The electron needs to absorb enough energy to get to the next energy level. Okay, and we'll talk more about that in the next lecture. Okay, but essentially what we're saying is, okay, so let's make a few key points about this model. So the levels of increasing value as distance from nucleus increases. Okay. So these levels mean the electron's going to be further away from the nucleus. And that kind of makes sense because we knew the electrons like to hang out around the nucleus. So it's perfectly, it would make sense that these energy levels are moving further away from the nucleus, okay? So further away. Okay, further away from the nucleus means that the energy is increased, means increased or higher energy. Okay? So we can say electrons can travel away between levels by absorbing a photon of light, or in this case energy, by absorbing a photon of light. So a photon of light is basically light in the form of packets of energy. So they have only a specific quantity of energy that can be absorbed by the electron. So a photon is a particle. So it's a particle. It's pretty much a particle of light. The how light kind of it's interacting with matter. Okay, so this is another way of saying energy. Okay, so let's kind of draw what that will look like schematically here. So I'm going to draw up here. So say we have the n equals 2 level and the n equals 1 level here. Okay? All right, so say my electron is right here, or my particle's right here. A photon of light is going to be bombarded. So here's my photon. And this photon of light has a certain wave-like property, so we can also call this H, well, actually we haven't gone there yet, so not yet. So here's a photon, okay? All right, so when we say plus photon here, what happens is the electron now will travel to the first excited state. So here's my electron now. So let's just mark this as an electron. So here's my excited electron. It's in the first excited energy level. So the n equals 1 is the lowest energy level, and we call that the ground state. Okay? And then eventually we're going to lose a photon here. So we're going to then what happens is the electron will relax back to its original state and lose a photon. So in this case, then it will fall back down here to the initial level. Right here. And what happens is it's going to give off the photon of light. So this is the photon, and then this is what we see as light. Okay, so the energy we see pretty much from light is this, the electron is giving off this photon, and that's what we perceive as light in reality. Okay, so that's what we see. So we can say light we see. Now that's if this photon has a wavelength in the visible spectrum. So it could be light we see it. So light we see if in visible light, invisible. Let's just say if visible light. Okay? So one thing we could say is that, okay, absorbs a photon, it's going to get promoted to this next highest energy level, and then when the electron, so now excited states are not observed for very long, so it'll tend to fall back down here to give go back to the initial state. So this is called, when we lose a photon, this would be called emission of light, and this would be called absorption. So when the photon's absorbed, we gain energy, so we're higher energy, and then when a photon is lost, we emit a photon light, so we're giving off light. Okay? All right. So now if we take a look at this diagram here, so before Bohr, there were these series of energy levels developed by other scientists. And you see here that they kind of document the energy transitions between the higher order energy levels. N equals infinity, 8, 7, 6, 5, 4, then 3, 2, 1. And you see the trend here that the first transition is the highest in energy because, or I mean, the difference between energy is highest between the first and second energy levels, and that's because it takes a lot more energy to remove an electron or promote an electron from its ground state, because that's where it's closest to the nucleus. So the force of attraction between the protons and electrons are going to be the strongest there. So once you get past that initial ground state, the energies get less. The energy differences get less because they are getting further away from the nucleus. So the nucleus, the influence of the positive charge from the protons are going to diminish over a longer distance. Okay, so this is just a diagram I wanted to show to illustrate that the energy levels here, see how they're specific gaps. So in this case, we say the energy levels are quantized, or they have specific values that unless you have the right amount of energy, you can't bridge the gap and you can't go to the next energy level. So that's how we kind of think about this in terms of the line spectrums here. These specific lines represent specific energy levels, and if we look right here, we can see that each value here represents a not only an energy value, but also you see these lines here. They do represent some of the line spectra that we saw in the hydrogen atom. Okay, so they do have some. There is a connection between them. That these lines are representative of the energy levels in the hydrogen atom. So namely that these transitions were falling from higher energy levels to the n equals 2 level. And the first, I believe the first energy level, so you see here, these are transitions between pretty much the higher energy levels, because those will take less energy to travel between. And we see here the n equals 1 and 2 level, and that's about the wavelength of light will be 121. So something pretty much in the close, I think, like close to ultraviolet, or something that's really we can't really do using visible light. So it won't be visible light. It will be actually higher energy form of light. Okay. So that's pretty much how the energy levels are structured in the atom. So that's an introduction. We'll definitely go over more of it in the next lecture. But let's move on now to the next subject here. Okay. All right. So now, we know the wavelength, right? And we know the frequency of light. So how do we calculate the energy? Well, it turns out that energy is directly proportional to the frequency of light. So the frequency of the wave of light is going to be determines energy. So the higher the frequency, the higher energy that light will be, or how that light will have higher energy. So we can use this equation here. Energy equals h nu. So nu is frequency, h is Planck's constant. So Planck determined that to relate energy to its frequency, there was a constant associated with every type of light, and that's known as Planck's constant. So a very important contribution. Okay, and it shows that the energy of a photon of light is directly proportional to the frequency of light. And then to relate the two, right? To relate the two in this equation, you need a constant. So there's always some value that will always be, the E divided by V will always equal to some constant, and that has to do with the relationship between energy and frequency. So the units are usually joule seconds, joule times seconds. So using this equation, Bohr was able to calculate the energy levels of the hydrogen atom, and he could basically point out, like, oh, this is where this line comes from in the hydrogen spectrum, this is where this line comes from, and it has to do with these specific energy levels within the hydrogen atom. So even though the hydrogen atom is so small, it has this structure inside the atom that was fascinating at the time and still is. So we're still trying to understand the implications of, you know, quantum mechanics and what we can use it for. Okay? All right, so now let's do this exercise here. Okay, so let's calculate both the energy of a single photon of red light with a wavelength of 700 nanometers and the energy of 1 mole of such protons. Okay, all right. So from the equation above, we know E equals h nu. Okay. So E in this case would be Planck's constant, 6 times 626 times 10 to the negative 34th joules second. All right. And then we need to calculate the wavelength first. Okay? Well, no, the frequency. So if we think about this, we calculated the frequency in the previous problem, right? So let's go back to our problem here. We saw that the frequency for 700 nanometers is 4.283 times 10 to the 14th. So let's copy that value here into our equation. 4.283 times 10 to the 14th joules seconds. Okay. Now, okay, so now we can say that we have 2.838 times 10 to the negative 19 joules per photon. So this would represent joules per photon. Okay? So another thing we can do is this equation can also be represented as, so we know that wavelength times frequency equals c. So we can actually substitute, we can actually solve for nu here, where nu equals c over lambda. So now this equation right here, E equals h nu, we can represent that a little bit differently. We can also say energy equals h times c divided by lambda, like that. Because here we plugged in lambda, we plugged in this equation, lambda equals c over wavelength. So if we do that, we can actually solve now without having to solve for the frequency. Okay, so that's another way we could solve for that. So if you just input the value here, that should give you the same answer. Okay, so we can do that as well. So if you don't want to calculate the frequency by itself, you can go a shortcut way and just say, okay, I'll time h by the speed of light divided by lambda. But you have to convert lambda to meters, or else you'll get the wrong value. So it might be just faster to calculate or just put in the value for the frequency. Okay, so that's per photon, but now we want to know per mole of photons. So we have to consider Avogadro's number. So we're going to take this value here, 2.8 38 times 10 to the negative 19 joules. Okay, so this is per photon. For one photon, okay? Now we know that just like for amount of atoms, we're going to say 1 mole of photons is going to be equal to Avogadro's number. So 1 mole photons is equal to 6.022 times 10 to the 23rd photons. Okay? And when we do that, we're going to get a big number now that's more representative of an energy for mole photons. So when we work as chemists, we like to think of things in moles because that's like what we like to work with. So it's going to be 1.709 times 10 to the 5th joules per mole. Okay, in this case, photons. And then we can, if we want to write it in kilojoules, we can also write it in kilojoules, and this would be 170.9 kilojoules per mole. So usually when we represent like energy or something, it's usually in kilojoules, especially if we have a big number. So to give you some kind of, give you a point of reference, this is enough energy okay? This is enough energy to raise the temperature of 1 liter of water by more than 40 degrees Celsius. So that's a lot of energy, okay? So that's kind of give you a, kind of a frame of reference, like how much energy this is. Like this is a lot of energy because it can raise the temperature of 1 liter of water by 40 degrees. So that's a lot, okay? So that's how we calculate the energy of, say, radiation. If we're given the wavelength, okay, we can also calculate the energy. All right. So since the energy of radiation is proportional to the frequency, we say that the radiation of high frequency has high energy, and radiation of low frequency has low energy. So this is why, if you think about, cell phones, they emit radiation too, and the source of radio waves because it's communicating with a radio tower. So the reason why we can be stuck, have cell phones stuck in our faces, or look at it every day, and watch TikTok videos or YouTube videos on it, and we don't really get sick from it, and it's because the energy associated with radio waves is small. It's smaller than ultraviolet light, smaller than colored light, and much smaller than looking at TVs or microwaves, so you won't get sick from it. So it's relatively unharmful to us. So that's why we can be around it. Okay? And we don't really have to wear any kind of protection. And that's because the energy associated with such a long wavelength form of light radiation is not harmful to us, and that's because there's virtually the energy. There's virtually not a lot of energy that hits hits our bodies when we're viewing a computer screen or our phones, stuff like that. Okay. So the last thing I want to talk about is the wave character of matter. So I won't create a fourth video at this time. I'll just stick to 3. Okay. So what I just told you, like absorbing a photon, emitting a photon, that was kind of what we described as the particle nature of light. Electrons can absorb light in the form of photons, and then that has a specific amount of energy and emit them later on as a photon of light as well. So we call those packets of energy, or you can like quanta. So a specific quantity. Okay, but now let's talk about the wave character of matter. So Louis de Broglie described the wave character of matter by suggesting that an electron could be described by a wave. And if you think about it, moving electrons emit light, just like how it emits light when it falls back down to the ground state. So it kind of makes sense that this light can also have wave properties. And you kind of think about like objects, like water molecules making a wave in water, and then like anything you can think of that kind of exhibits a wave. Matter has both wave properties and particle properties, and we have experiments that can support this. Okay, all right. So in this equation, we have the wavelength is equal to h over mv. And what this means is that h is Planck's constant, m is the mass of the particle, and v here is not frequency, it's velocity of the particle. So in this case, we can use this equation to calculate the wavelength of any particle. So it can be... So if we have a really massive object, well, our wavelength is going to be really large in a sense. So in this case, I think in this case we would have to, so if the particle is really large, it's going to be, you're going to get a bigger, we'll actually go over some examples, but if you do, so larger objects tend to have bigger, larger or longer wavelengths, and that kind of suggests, okay, if it has a larger wavelength, it tends to behave not much like a wave, because remember, the longer the wavelength is, the slower it moves as a wave. So it makes sense that larger particles or larger objects behave more like particles than waves. And that makes sense, right? Because like if you toss a heavy object, right, it's just going to fall down like a heavy object, or like a particle. It'll just move, stop, and then behave like a particle, right? It behaves more with its mass. Now, an electron is really light, so it'll move faster. So by that comparison, we can say, okay, smaller objects or smaller particles tend to behave more like waves because they're moving faster, and then they're harder to detect, right? So they kind of move like what waves do. They oscillate really fast and they're emitting energy. So usually small particles like electrons, they behave more like waves, and larger particles, they more behave like everyday objects, like a ball or a car. Okay. All right. So an experiment that was used to show the particle nature, or the wave nature of the electron, is Young's double slit experiment. So essentially what happened is this experiment is very important, and it was done such a long time ago, but the implications are still very much important today. So you have a light source, and then when the light source shines through a screen with some narrow openings, what happens is that the light gets diffracted, and through these two openings, the waves will start to generate new waves, and then those waves can superimpose on each other, or what we call interfere. So what happens is when they interfere, you're going to get a interference pattern. If we view the result of the wave on, say, like a black screen, okay? So you're going to get this interference pattern where you have areas of dark spots and areas of bright spots. So what happens is that these waves tend to either have destructive interference, like this, when the waves are they kind of look like a DNA coil, but they're kind of, the waves are kind of like oriented 180 degrees. So every apex is going to have a corresponding trough of the other wave. So they're kind of superimposed, where it's like a mirror image of each other. Like so. And that's called destructive interference, when the signs of the waves are opposite, so they cancel each other out. Now you're going to have some areas of constructive interference, where the two waves superimpose on each other like exactly, and they kind of give rise to a bigger effect of the wave, and that's the bright spots we see in this pattern here. And what happens is that you get a diffraction pattern where you're going to have areas of high intensity, no intensity, high, low, high, low, high, low. So it's kind of going from one maximum and then one minimum. And that has to deal with pretty much this interference pattern here. So you kind of see the pattern there, that light, the electrons, they behave light, electrons, the light source, they're moving electrons, right? So they behave like waves. So that was one kind of evidence for the wave nature of light and electrons. Okay. And then we could kind of see the example in real life, what water droplets, they make waves in water. And if you kind of look at these images here, you can kind of see areas where they overlap. So it's more likely to say that matter also has this kind of wave-like property, which allows us to explain why electrons can absorb light or give off light. And that's because there's also a wave-like part of light that exists in our world. Okay. All right, so everyone, that's it for this lecture. I will see everyone in the next set of videos, where we'll talk more about quantum mechanics. Okay, so I'll see everyone next time.